All right, so now we're ready to do section 4.6, which is about our next technique for integration called integration by parts. So let me introduce that with an explanation. So integration by parts is used to handle many types of products. Like you're trying to integrate a product of two functions. So it's kind of like a product rule for integrals. It doesn't work for every product, but we'll see. So, but it comes from the product rule for derivatives. So let me show you what I mean. So this is a review again. So suppose I wanted to take the derivative of a product. Now I'm going to write u times v. U and v here are functions of x. I want to keep the amount of notation to a minimum, so I don't want to write u of x, v of x. So u and v are both functions of x. So we do the product rule by taking the derivative of one function at a time and leaving the other one alone. So we'd have u times dv dx. So dv dx is by definition the derivative of v with respect to x, plus the second half of our product rule, v times du dx. Right? So now we integrate both sides. So this was the review. That's just the product rule for derivatives. But now if we integrate both sides, so I put an integral symbol on everything with dx after it. Well, when I integrate a derivative, that gives me those two things cancel. When I integrate the derivative, they basically cancel. So when I integrate the left side, I'm just going to get uv back. uv equals the integral of the whole right side. Let me separate it though across this addition. So integrate. Now just for convenience, let me cancel these dx's just to make it easier to write. So dv over dx times dx, that basically gives me dv. So this will be the integral of u dv. Likewise, this one will be the integral of v du. But everything here, so the u, the v, dv, and du, those are all things that really involve x. These are just like stand-in letters to represent more complicated expressions. Okay, so I get this equation, but I want to turn it into a formula that helps me to actually integrate. Okay, so what I'm going to do is solve this equation for integral of u dv. The integral of u dv will equal uv minus this integral. V du. Okay, so I just took this equation I got and I isolated the integral of u dv. Alright, so this is our key formula. This is the integration by parts formula. Right, so I'll leave it on the board for this next example, but you're going to want to have this handy, so make sure you copy that down and have it in a place where you can see it for this entire video, because we're going to be using it again and again. And in normal situations, I would have you memorize it for the test, but like I said, our tests are going to be some form of at-home test, obviously. So you'll have your open notes if you need them. But this is a very important formula for integration. So let's do a simple example just to illustrate how this works. So we use this primarily in situations where we're trying to integrate a product. So let me say it like this. Let's do this example. Integral of x e to the x dx. So I've got an integral of x times e to the x. There's a product. Now, in some products, like we saw with substitution technique last time in the previous video, sometimes you can make a substitution to get rid of that product. But this one, I don't really have an inside function anywhere, so I can't say u equals anything. If I do u equals e to the x, that's not going to help me with this x. So I might be able to make a substitution, but it's just going to be like rearranging things into a different form that still isn't easy to integrate. So there's not really any convenient substitution to make here. So instead, I just want to treat this as a product, and for products, I want to use integration by parts. So what I'm doing is the left side, this side of my integration by parts formula, the integral of u dv, that's the integral that I'm given. So that's this. So what I need to do is figure out which part of this integrand is u, or should be u, and which part is dv. So here's the way I think of it. I want to set up 4 boxes. I need to look at this and figure out which part of this is u and which part is dv. Now, one thing is the dx is always part of dv. So that dx has to be part of dv because that's the differential part. Alright, so there's basically 2 functions, x and e to the x. One of them will probably be u and one of them will be the rest of dv. So I could put x here and e to the x here, or I could put e to the x here and x here. So there's kind of a trial and error issue with which is the correct choice. Okay, so after I make my choice, then I have to figure out what is du and what is v, because I need v and I need du when I apply this formula. Okay, so I need to fill in these 2 parts and then figure out what the other 2 parts are. Okay, so let me just do it the right way first, and then we'll go back and see what would have happened if I did the opposite. Okay, so for this specific problem, the right choice is u equals x and dv equals e to the x. So I make that choice. Then I figure out what is du. Du will be the derivative of u. So in this case, that's 1 and then dx. If I have dv equals e to the x, v will be the antiderivative of e to the x. So the integral of e to the x. To get rid of the d, I integrate. So integral of e to the x is e to the x. Okay, so these 2 boxes I have to figure out based off of my original choice. Okay, so let me write it down here. So after I make this choice, then I rewrite my integral using my integration by parts formula. So it's u times v. So u times v would be x e to the x. And then it's minus the integral of v du. E to the x times 1 would be e to the x times dx. Okay, so we've applied our integration by parts formula. There's still an integral that we have to deal with, but if we chose correctly here, that new integral should hopefully be easier than the original integral. And in this case it is. X e to the x is difficult, we don't know how to immediately integrate that, but e to the x is a simple function that we do know how to integrate. So we can finish this. x e to the x is already done, minus the integral of e to the x. Integral of e to the x is still e to the x. And once we finish that last integral, and there's no more integral symbols to deal with, then we stick on our plus c if it's an indefinite integral. And so that's my final answer. Right? So we're done with the problem, but now let me go back and illustrate, because there was a choice we had to make. What would have happened if I'd made the opposite choice? All right, so this is the correct answer. Let me go back and erase all of this. Okay, so going back to my integration by parts choice, again, I need to pick what is u and what is dv. So let's do the opposite choice now. Let's make u e to the x and dv x dx. The dx has to be part of dv, like I said. Well, then du is the derivative of e to the x, which is e to the x. Stick on a dx with it. If dv is x, v would be the antiderivative of x, which is 1/2 x squared. So we have our four ingredients now. Let's apply our formula. U times v would be 1/2 x squared e to the x. So e to the x times this, I just wrote it in a convenient way, minus the integral of v du. V du would be 1/2 x squared e to the x dx. And so I applied the integration by parts formula. This is equal to this, but the catch is I still have to integrate this. To get to my final answer, I have to integrate this new integral, and this one's harder than the original. I had just x e to the x. Now I have x squared e to the x. It's a more complicated function. So that tells me, I just compare my new integral to my original integral. The new one's more complicated. That means I'm headed down the wrong path. If I tried this one first, that would suggest to me I should go back and make a different choice for u and dv. Make the opposite choice. Okay, so frequently on these integration by parts problems, for the ones we deal with, there are kind of two clear choices. So I could do it this way, or I could do it this way. One of them will tend to be the right way, and the other one will make things worse if I use it. So there's a little bit of trial and error with it, but if you try one way and get something harder, you immediately go back and try the other way. Okay, so let's talk about. We'll do more examples. Again, just like with substitution, this takes practice to get used to making the choice and applying the formula. But let me give you some rules of thumb first for how to make the choice. So have the formula written down in front of you. We're going to be using it again and again. I don't want to waste the space on my board to leave it there, though. Okay, so here are kind of some guidelines. dv. So when I choose dv, we have to be able to integrate dv. So if I have dv, I have to be able to figure out v. So whatever dv is, it needs to be something I know how to integrate. And we can't integrate every function. And for example, logarithms, if a logarithm appears in your integral, we don't have an integration rule for log. So I don't know how to integrate ln x. So ln x would be a bad choice for dv at this point. So this has to do integration by parts. Whatever dv is, it has to be something I know how to integrate. Secondly, maybe both choices I would be able to integrate, but we prefer it to get simpler when we integrate it. So on the last example I did, I could make the choice dv was e to the x or dv was x. When I integrated x, it became x squared, or 1/2 x squared. That's more complicated, so that's bad. When I integrate e to the x, it's e to the x. So it didn't get any worse. So that's better than getting more complicated. Ideally, we want it to get simpler. That's, I guess it's, yeah, ideally we want it to get simpler. That's fairly rare for something to get simpler when we integrate, but we at least don't want it to get worse. We don't want to get more complicated. Okay, so then on the u side of things, the considerations about u, well, we have to be able to take its derivative. That's not really a problem. Any of the functions we know we have a derivative formula for it. Any of the basic functions, I mean. So that's not really a consideration for the kinds of examples we look at, but we prefer it to get simpler when we take its derivative. So if I have u, I need to figure out what is du. I want du to hopefully be simpler than u was, or at least not worse. Okay, so this is kind of the main rule of thumb. The non-negotiable thing is whatever dv is, we have to know how to integrate it, and that can be a sticking point because there are certain functions we don't know how to integrate. So that has to be true. Then once we have narrowed it down to what is allowed to be dv, then we want to make a choice so that dv gets simpler or doesn't get worse when we integrate, and u doesn't get worse when we take its derivative. Okay, so let's do some more examples. Alright, so suppose we had the integral of x squared ln x dx. It's a product that I can't simplify my way out of. I can't make a substitution, really. So that's integration by part. That suggests that integration by parts is the right choice, right method to use. So I need to pick u and dv. Okay, so again, there are kind of two clear choices of functions. I've got x squared and I have ln x. So let's first think about which ones am I allowed to put as dv. So I'm allowed to put x squared as dv because I know how to integrate x squared. Ln x, if I put ln x here, we don't have a formula for the integral of ln x. So if I did that, I put dx. If I did that, I don't know how to integrate it to find v. So that's a dead end there. I'd be stuck. So that means by process of elimination, I basically have to put x squared here. Now, I say that it's possible that there might be some non-obvious choices. Like maybe I would just want to put x there and put x ln x, the remaining x and ln x here. That might be something I could do, but let's try the obvious things first. You don't want to get into weird choices like that unless you absolutely have to. I put x squared as dv. That means ln x is u. Okay, so that was kind of forced on us here. Then you think about, is this a good choice? Well, in this case, it's pretty much the only choice, but let's think about our other guidelines. dv if we integrate that, well, the integral of x squared is 1/3 x cubed. And so that's not a good sign. That violates one of our guidelines. However, it's the best I could do because of the first guideline that we have to be able to integrate whatever dv is. So it got more complicated, and that's maybe it seems bad. Let's see what happens though. If I take the derivative of ln x, so du, the derivative of ln x is 1 over x times dx. And this is more of a qualitative question. Is 1 over x simpler than ln x? In my opinion, and probably most people's opinions, yes. It's no longer a logarithm function, it's now a power function. And those are simpler than logarithms. Simpler to deal with, I should say. But really what you're hoping for is that the product, so the product that we started with was x squared ln x, so it's this times this. The new product that we'll have in our new integral will be the product of this and this. And now those are the same kind of function. It can be simplified when I multiply those two. So I'm trading my original product integral for a different product, and that new product is simpler. Okay, so now let's do the integration by parts formula. U times v would be 1/3 x cubed ln x minus the integral of v du. So that's 1/3 x cubed times 1 over x dx. And the point is, this new integral, we can simplify it. It's a product, but it simplifies to just a simple function. So you got, then you note, so I'm just going to change it. X cubed divided by x, that's x squared. So we have 1/3 x squared as our new function. And that I can integrate. It becomes x cubed. I divide by 3 again, and I get 1 over 9 plus c. Right. So for us, if you're trying to integrate something involving ln x, unless you can make a substitution where u equals ln x and it disappears, if you decide that you're using integration by parts, then ln pretty much has to be part of the u. As we'll see, it's possible you could put it as dv once we know how to integrate ln x, which is my next example, but it becomes much more complicated when you integrate ln x. So ln x is just, if you see it and you're using integration by parts, it's going to be up here as part of u. Okay, so let's do the integral of ln x. So this one is a little bit tricky, or it's a little bit deceiving. It doesn't look like a product. There's no product going on, no interesting product happening here. But we still can integrate this using integration by parts. So u and dv. Like I said, we don't know how to integrate ln x, so I can't put it as part of dv. It has to go as u. And that leaves me with just dx. That's the only other thing. So that's like 1 times dx. dv is dx. So now let's figure out the other two ingredients. If u is ln, then du is 1 over x dx. And if dv is if dv is dx, then v is the integral of 1. So put 1 there for clarity. Integral of 1 would be x. The antiderivative of 1 is x. So, yeah, it got more complicated, but just like the previous example, v and du combined will be something easy. So we get u times v is x ln x minus the integral of v du x times 1 over x is just 1. Antiderivative of 1 is x, so we get x ln x minus x plus c as our final answer. Okay, so now technically we know how to integrate ln x. The antiderivative of ln x would be x ln x minus x. That doesn't mean that I would ever want to put ln x as dv, because this is much more complicated than ln x. It would blow up my new integral and make it that much more difficult. So it would still be a bad idea to ever put ln as your dv part in an integration by parts problem. All right. So let's do a couple more examples to illustrate other issues. So the integral of x squared times e to the 3x dx. Again, this is a product, so integration by parts seems appropriate. Let's make our choice. So I need to pick u and dv. This time, our two functions are x squared and e to the 3x. Both of those functions we know how to integrate. So now we have multiple choices to decide between. Either one of the functions could be dv. So that first guideline, that's not an issue for this problem. So then we want to pick things so that things get simpler when we find the missing ingredients. So u could be x squared. Its derivative is 2x. That's simpler than x squared because the exponent goes down. The derivative of e to the 3x would be 3 times e to the 3x. That's not any simpler. It's not really any worse. So on the u side, we'd prefer to put x squared there. Okay, but let's not do it just yet. On the v side, on the dv side, if I put x squared as dv, its antiderivative would involve x cubed. It would be 1/3 x cubed. That's more complicated, so that's bad. If I put e to the 3x there, its antiderivative is still going to involve e to the 3x. It's going to have a constant, but it's still going to be essentially e to the 3x. So it's not any worse. So e to the 3x, it doesn't really care which side it's on. X squared would rather be on the u side because it gets simpler when you take its derivative. So that suggests that we should put x squared here and e to the 3x here. E to the 3x dx. And then we make figure out our missing pieces. Du would be 2x dx. V would be the antiderivative of e to the 3x, which is e to the 3x divided by 3. Right, because we anti-differentiate e to a power. You divide by that coefficient in the power. You keep the same exponential function, but you divide by the coefficient up there. All right. So now we made our choices. So our integral with the integration by parts formula would be u times v. So I like to put the coefficient in front. 1/3 x squared e to the 3x minus the integral of v du. So that would be 1/3 times 2 is 2/3 x e to the 3x dx. Okay, so now you write out that formula and now ask yourself, is it headed in the right direction? Well, we went from x squared e to the 3x to 2/3 x e to the 3x. The 2/3 is a coefficient that wasn't there before, but that's just the coefficient. That's just a constant multiplier. It doesn't really affect the difficulty of the integral. So that looks worse, but it isn't really worse. the important thing is we went from x squared to x. So the type of function got simpler. An exponent decreased, that's good. So that tells us we're on the right track, but we're not done yet. We still have to integrate this, and the way to integrate this is it's a product, so we use integration by parts again. So I'm going to run out of space here. Let me go ahead and I want to keep the original problem. So let me put the current state of things up here on the same line. Okay, so let me erase the previous integration by parts stuff. So I used integration by parts once. That turned my integral into this. I've got 1/3 x squared e to the 3x. But now for this integral, I need to use integration by parts again. So I need to pick a u and a dv. I mean, need more space than that. All right. So again, I've got two main parts, x and e to the 3x. For the same reasons, e to the 3x doesn't care where it goes, but x would rather be u because it gets simpler. Powers of x get simpler if they're positive powers of x when you take its derivative. Another thing I should say is when you have to use integration by parts more than once in the same problem, you kind of don't want to switch your choices. So the first time I used integration by parts, u was the power of x, and dv was the e function. So the second time I use it, dv should still be the e function, and u should still be the power of x. So it's a different power of x, but it's still the power function part of the product. If you switch, if you change your mind and for the second integration parts you switch your choices, you'll end up going backwards. You'll get back to the original integral, and that's bad. We don't want to go backwards in our steps. All right, so I'm going to make u equal x and dv equal e to the 3x dx. Now there's a couple things I could do with this 2/3. One thing I could do is pull the 2/3 out and just multiply it times the entire integral. Or you could attach it to one of these. I like to attach it to the x just because that's the simplest place to put it, I think. So if I do that, then du would be 2/3 dx, and v would be, again, 1/3 e to the 3x. Okay, now I'm going to need some more space here. Let me move the next line down. So now this becomes, I've already got 1/3 x squared e to the 3x. Then I have minus this integral. This integral gets replaced by the integration by parts formula. So it's a good idea to replace it with parentheses. Inside that parentheses, you're going to have u times v. That would be 2/3 x times 1/3 e to the 3x. That would be 2/9x e to the 3x. Minus, still inside this parentheses, minus the integral of 2/3 v times du. So that would be 2/9 e to the 3x dx. Okay. So it's important that this minus sign here is applied to the entire thing we just replaced the integral with. So if you want, you can distribute this minus sign. So minus this, minus this. That'll make this minus a plus if I get rid of the parentheses. So let me do that to keep things a little bit neater. I'm going to distribute this minus sign. So when I erase, I get minus 2/9 x e to the x plus this remaining integral. All right, but then I still have one more integral to handle. I still have an integration symbol. So not quite done. The good news is this new one, it no longer requires integration by parts because there's just a single function. It's just e to the 3x. And I know how to integrate e to the 3x. I've already done it multiple times on this same problem. So our final answer would be all of this preceding stuff plus when I integrate this e to the 3x, I get e to the 3x divided by 3 again will make this 2 over 27. And now with that final integral handled, I can stick on my plus c at the end. All right. So integration by parts, it's frequently a technique that you have to apply more than once in the same integral. And the idea, the hope is every time you apply it, that the new integral is one step simpler. So like we're reducing the power each time we apply it. The power on the x gets smaller each time until x is gone. And when you have to do it more than once, the big thing to pay attention to is be very careful about the signs. Each time if you apply it, you have a minus sign from the previous step, but then you get a new minus sign when you get the new integral, so make sure you distribute minus signs correctly. All right. I want to make 2 more points. We basically have these 2 techniques now, substitution and integration by parts. If I had a problem like this, integral of x times e to the x squared, let's think about how we'd want to do this. This is a product, x times e to the x squared. It looks like the previous 2 problems, a couple of the problems from this video, but this is not an integration by parts problem because what we also have is an inside function, e to the x squared. So x squared is an inside function, and its derivative is 2x. And we've got an x there. So the right way of doing this is just use substitution. Not integration by parts. So before you jump, in this current section, 4.6, I lost track of 4.6. In this current section, integration by parts, we're kind of trained ourselves now to treat products as integration by parts problems. But it's really, if ordinary substitution doesn't work, or if simple algebra doesn't allow us to simplify our product, that's when you try to use integration by parts. So you look for substitutions first. Here, the substitution would be u equals x squared, and then du is 2x dx. So my integral would become 1/2 e to the u du. And that's 1/2 e to the u plus c. So 1/2 e to the x squared plus c. If you tried to do integration by parts for this, your 2 functions are basically x and e to this power. Well, e to this power I can't integrate, so I'd have to put that as u, and that would make dv equal x, but when you integrate it gets more complicated. So integration by parts is going to take you in the wrong direction. There's no way to make integration by parts work for this problem with the techniques that we have. Right, so just want to emphasize that if you're just integrating things and you don't know what section they come from, don't jump to integration by parts too soon. Look for simplifications first, and look for simple substitutions that might work. All right. My last point for this section is just, let's just do one example where it's a definite integral. Let's integrate x times e to the 4x from 0 to 1. So there's, again, kind of two ways you can think about this. It's definitely integration by parts. Let me do my choices over here so I can do more work here. It's very similar to the one we just got through doing. Again, e functions, as long as it's just a simple exponent there, e functions don't care which side you put it on. X to a power prefers to be on the u side if possible. So we want u to equal x and dv to be e to the 4x dx. And that means du is 1 dx and v is 1/4 e to the 4x. Okay, so now we apply the integration by parts formula. uv would be 1/4 x e to the 4x minus the integral of v du, so 1/4 e to the 4x dx. Okay, so that's what we do when it was a indefinite integral, when we didn't have the numbers on the integration symbol. Now, since we do have numbers this time, it's a definite integral, we can approach it two different ways. We can either continue the way I'm doing it, just ignore the numbers until the very end, when you've finished all the integration and you've got a final function involving x, then just plug in these numbers to that whole function and subtract. That's fine to do it that way. The disadvantage would be, and it probably won't really come up for us in the kinds of examples we look at, but the disadvantage would be sometimes these new integrals, like the new ones you get, when you get to the later one, it might require like a regular substitution to integrate. So maybe at that point you have an integral you want to tackle with a substitution, so you want to make a change to your variable, so you'd make a change to your bounds. But that new change would only apply to that latest integral. So the earlier stuff would be in terms of x, the new stuff would be in terms of u, a different variable, w say. I don't want to use u if we're using parts. Like a w integral. And so you'd have different w values instead of the x values. So if you think of it that way, then the way I think of it is, anytime you use integration by parts, this uv part, that's escaped the integral. It's ready to have stuff plugged into it. So I want to plug in 1 and 0 for this. The new integral, before I do any changes to it, the new integral will have the same bounds as the previous integral, so 0 to 1. So I could then plug in 1 to this, so 1/4 times 1 times e to the 4 times 1, and then plug in 0. And whether or not I'm done with the next integral or not, I could simplify this and get a number out of it. So that would be 1/4 e to the 4th. This would be 0, so that goes away. So I could evaluate this part and get a number for it, and then just worry about the rest of it. So let's do this. Integral of this would be e to the 4x. I have to divide by 4 again, so 1/16. And then plugging in my numbers, but I still have this minus sign in front of it. So I need to be careful. It's minus parentheses 1/16 e to the 4 minus 1/16 e to the 0. E to the 0 is 1. Minus minus makes this plus 1/16 times 1. And then I can simplify the e to the 4ths. This is a like term, so I could subtract their coefficients. 1/4 is 4/16, so that's going to be 3/4 e to the 4th plus 1/16. If I want the exact answer. If I don't care about exactness, I can plug that into a calculator and get a decimal approximation. right. So that's integration by parts. That's with a definite integral example. So to summarize, we've now finished sections 4.5 and 4.6, integration by substitution and integration by parts. So that's homework 12. Like I said in the previous video, or a previous video, section 4.7 is about integration by using tables. I just realized my microphone wasn't plugged in for this video. We'll see how bad it is in the post-production. 4.7 is integration by tables. That basically just means you look at a table of formulas and you try to match your integral with a formula from a table. I don't know how I would teach it without having like an overhead to refer to a standard table all alongside everything I do here. So I'm just not going to cover that section. So you can ignore what I say, the last few problems of homework 12, problems 15 through 19. You can just ignore them. Don't even do them. I will make sure to adjust your grade accordingly. You don't need to worry about the grade on it. So that's homework 12. So I'll make sure the sound is good enough on this video, and if not, I will have to re-record it, I guess.